quarterly. How much should my initial deposit be? I want to work backwards. In this case, I'm going to solve for my initial amount, my principal. If I wanted to end at $4,000, that's going to be how much is left over in the account after that amount of time. This is working backwards. So I want $4,000 at the end to equal, well, some amount, don't know how much, at 1 plus my rate, 0.65, quarterly. How many times a year does it go? 4. And I want 4 times 7. Now, if you think about it, this really is nothing more than basically it's a one-step equation. But what do you have to do? Yeah, because this is X, your amount, times a whole bunch of junk. All I gotta do is figure out this junk. It'll give me some number. So if I figure that out, I do. So if I do 1 plus alpha y equals 0.065 over 4, hit enter. And I raise that to the, well, what's 4 times 7? 28. That's some crummy decimal. But it's that crummy decimal times x.
So
How do I undo it? Divide. So I have to take 4,000 divided by the crummy decimal. You guys remember how to use the answer key on your calculator? This is where using that answer button is really, really, really helpful. I should deposit $2,547.09 if I want my money to be $4,000 in 7 years. Yeah, how much you want to invest. So the idea here is that if you guys start to think about, saving money for graduation or down payments on things and stuff like that, if you start going to banks, you start to think about, okay, what kind of interest rates do I get for certain types of deposits, certain types of investment type things. This is the kind of idea that, hey, I want to have $10,000 to help with a down payment towards something after I'm done with college. Well, right now, you guys have a couple years left of high school, and you probably have 4 to 5 years of college then. So there's your idea right away, is that if you wanted to have $10,000 saved up after you get done with college, in, let's say, 7 years, well, what type of accounts are available via banks nowadays that you can deposit and earn certain interests? I don't think savings accounts aren't going to earn you a lot of interest. You'd have to use one of the other types. I don't know, something. But that's the idea, that you'd have to go. You could figure out, well, how much would I have to forego over now to have that much later? It's just working backwards, pretty quick. Any question on that?
can we go over number 2?
The one in the back?
Yeah.
Mark makes an investment of $500 and an account pays 6% compounded monthly. Write it out.
So 500 times 1 plus 0.06 over 12 times, to the 12 times t power.
Yeah. That's exactly it.
They're both about 8. So then if you do it like by year, would T be 12 because 12 months, or 1 for 1 year?
1 year. Generally, this is time in years because it talks about a number of times it compounds yearly.
Okay.
So that t value will always be years.
Well, the original question says compounded monthly.
Right. Yeah. Well, that just means n is 12. How many times does it compound in a year? 12. That's all. Now, if it was 5 years, then it would be 12 times 5. That means 60 times it would have compounded. In 1 year, it only compounded 12 times. 2 would be 24, and so on. That's where this comes from. Now, there is part C on here, talk about effective annual rate. we're not going to get involved with any effective annual rates. You can not worry about, I'm never gonna ask you, it's a different calculation totally. It's not this 6%, it's something completely different, all right? So don't worry about ever being asked, what is your effective annual rate? It's gonna be a little bit different. Save that for later on. I love the loan shark question.
Let's do it.
The loan shark lends a gambler $1,000 to cover a debt, charges 35% compounding continuously. Oh, but we don't know how to compound continuously. So we'll have to wait on that one, because we'll start that one today, okay? Word problems, we okay?
Yeah.
I just don't know how to do the ones like every 4 years.
Which one? I'm so clogged up.
No, like these where it was like.
Oh yeah, and I promise you, and I was quickly ran them off, and I forgot that there wasn't a date on there. I promise you, I will have start dates.
I just didn't think that.
I promise I'll give you start dates. Okay. You did your homework. Merry Christmas. All right, let's talk about E.
Like, for this one.
Oh, like, yeah, I think so. So it was like
Did you say you did your homework?
Cool. So there's a number E, in case you didn't know that now. This number E comes from as, it's called Euler's number. Don't write all this out, but excuse me. As things compound more and more and more annually, as that value gets larger and larger and larger, it's always approaching this decimal E. 2.7963, 867, 525, 83467, 923. I just made all those numbers up. It sounded good. So it's kind of a constant. It's kind of like pi. It's irrational. It never ends. It's continuous. It just keeps going on and on and on. But it's an approximation. So as things, excuse me, they call it natural base E. As it compounds, as like I said, as the end value gets larger and larger and larger, it is approaching this value. So this is what we use for continuously compounding. That's why I told you don't worry about it, because I needed to show you the video so I can make your lives better. I know. So what happens here is you get, let me get to here. You get this expression E. And E can be treated just like any other variable. You could square it, you could cube it, you can do whatever. So if I had E squared times E to the 4th, what do you get? E to the 6th, okay. All those rules still apply the same as you would earlier. Just the same idea as, if it was pi squared times pi to the 5th, it would be pi to the 7th. So you treat it the same way, okay? It's not a big deal. What I want to get towards, though, about this whole idea of continuous stuff is that, excuse me, the formula changes ever so slightly for compounding interest. Okay? As you deal with compounding interest, then, I'm not going to worry about this one here. This was boring. Yeah, I'll skip over this. You get hurt. Your amount is your principal. Remember your initial amount. E, button on calculator. Is your percent as a decimal. And T is time in years. I thought we were dealing with amounts, it's LE. With principal, as in like the school
Like
principal,
school.
they want to be your pal.
Yeah.
When you're talking about money, I think it's LE. But remember, I have a degree in math, barely, but so I could be wrong about my English. All right. So the idea here is if you have a compounding continuously, you use per. Okay. If it's compounding monthly or annually, you'd use the other formulas because that tells you the number of times it goes through. All right. Like I said, this E is quite literally a button on your calculator. So if you go back to your packet that we were just looking at, there was it part D on that number 1, where it says, you know, $2,500 in an account compounding continuously at 0.7%. Your principal was 2,500. E, 0.7% would be 0.007, and I think this was for 4 years. And it is quite literally pressing the button. Okay. The E button, if I'm not mistaken, 2,500. See where it says LN? The third one up from on the bottom left. It's second, and this LN stands for natural log. Natural log and E are inverses of one another. Okay? Kind of like how you have square root and squaring, they're inverses of one another. Okay? So second, E, and it automatically takes you up, 0.007 times 4, and you press enter. There you go. That's how you use continuous. Continuous is very, very easy. Okay. Not much there. Also, E can play the role of, if you think about our exponential growth and decay, when we had the formula for exponential growth and decay, it looked like this: A times B, x minus h plus k. If B, it was growth if it was greater than 1. It was decay if it was less than 1, but greater than 0. Now is E growth or decay? Growth, because E is 2 point something. Okay? So you can graph E just like you would the other stuff. The only thing that's weird about graphing with E is that you're always going to get crummy decimals except for usually one value. And it's just an idea of what direction is it going from there. You can still do your shifts, your parent function, your shift stuff with your H's and your K's. You still have the same rules as far as your horizontal asymptote would always be at your K value and things like that. And I'll show you an example of this. Okay. Did I oversimplify or overthink that and assume that this is pretty straightforward about the whole idea of pressing a button for PERT? Well, let's show you this stuff then. Excuse me. So, like we said all this before, when you're dealing with E, it's the rate. I mean, obviously E is, as a base part, would be a growth, but in order to show that it, for E values for growth versus decay, it's not so much the B. When you're dealing with E, it's the R value. Okay, so when we're dealing with E then, we have Y equals AE to the R times K. So if the R is greater than 0, it's growth. If R is less, it's decay. That's the difference between your standard growth decay values, AB, versus E. Okay. Well, I didn't want you to write down all this other junk, all this stuff up here. It's basically I wanted this. This is how you distinguish between the two. All right. Growth and decay for the other one, it's the B value. Well, if we use the B value here, if I use my B value here, if we know that E is 2 point something, that means it would always be growth. Well, you could have E with a decay style. That's why they deal with it in terms of the rate. Okay. Excuse me. Now, remember, you're going to get crummy numbers, except for usually your intercepts, because if your value of x is 0, you're always crossing your y-axis. What do you think e to the 0 is? 1. So that's how you get your intercepts at A. Very similar to what we did here. If we had a parent, we use our parent function here with our AB to the x. If x was 0, our intercept was at A. The h and the k, we just moved it left and right, up and down with that value. Kind of do the exact same thing. To show you how we do this with just a point or two. Excuse me. So if I have the idea here of y equals 2e to the 0.75x. And I'm not going to use graph paper for this one because we're only going to get a couple of points anyway, so might as well just kind of fudge it. What's your R value? 0.75. Is that growth or decay?
Decay. I don't know.
Bigger than 0 here, 'cause it's growth. And you're thinking, and it's different because that's why we look at the R values, not B values. Okay. Excuse me. So it's going to be growth. Excuse me. If it's growth, remember it was doing this. Or if it was a negative A, then it would go that way. So we know it's going to look like this somehow. So you start thinking about, all right, what's the easiest way to figure this through? Well, where's my horizontal asymptote going to be in this case? Where's it going to be? Horizontal.
asymptote?
Where's my horizontal asymptote? No. What's your K value? There isn't one, so where's your asymptote? 0. Just like it was. Oops. That's close-ish. All right. You have an asymptote at 0. What's your y-intercept? 2. Not much going on here. Really isn't. Especially when there's no H and no K. If there was an H and a K here, what do you think I would have to move? Your intercept and probably my, what is that thing called? The asymptote. I forgot what it's called. Kind of important. Yeah, ish. Okay. Details, schmetails. All right, let's try another one. Let's try another one here. We use E, let's see, this one is e to the negative 0.5 times the quantity x minus 2 plus 1. Growth or decay? Decay. We know it's going to be a decay because it's negative. Okay. So we know that much. Excuse me. Now, our A value here is what? 1. The A value here is 1. Now, think back to what your A values meant before for directions. If it's decay and my A value is 1, is it going to be moving down to the right, or is it going to be moving up like that?
The top one.
The top one. Yeah, it's going to look like that. It has to look like that. That's what decays do if the A values are positive. All right. So now I go ahead and I try to kind of fudge my way through it. If I start this out, I know that I have a parent function-wise. I'm not going to deal with my H's and K's. That tells me I'm going to have a y-intercept where? At 1. I know I'm going to have a y-intercept at, excuse me, at 1 for my parent function. I also know that I'll have a horizontal asymptote. Let's do this better this time. At 0 to start with. All right. I know those two things to be true. I know that my parent function would probably look like this. But now I have to shift it. Which way does that have to go? Yeah. Right 2, up 1. So that means that this point goes right 2 and up 1, which means where is that point located now? At 2, 2. So this point now is at 2, 2. Where do I put my new asymptote? At 1. Bless you. And now to connect for this red one, what do I do for making a curve? Solid or dotted? It's really all we need to do.
How do you know that the horizontal asymptote?
Okay. Oh, it's sorry, the horizontal asymptote's at 1.
I meant, yeah, how do you know it's at 1?
K. Remember, you have asymptotes at K
Oh, right.
for growth to K styles. And it's the same thing with E's. Okay. Sir?
So when you want us to graph it, you want us to just kind of like leave out E?
Yeah. Oops.
So when you first graphed the parent function, you just like didn't pay attention to K?
No, we never do. And we shifted after that. It is pretty much that's really all there is to graphing these things. There's really no craziness or anything at all involved with it. All right. E1s are pretty easy. Oh. Anyway, that was bad. Let's see, that's another one. That's hurt. We did this. That's too easy. All right. Since 1972, the U.S. Fish and Wildlife Service have kept a list of endangered species in the United States. For the years spanning 1972 to 1998, the number of species S on the list can be modeled by 119.6 e to the 0.0917 t, where t is the number of years since 1972. What was the number of endangered species in 1972?
119.6.
It's kind of weird that they have a 0.6 of an animal, so let's just say 120. That feels kind of weird that, it was mostly alive, but partially dead. You can't say it was half dead. That's why we say it was mostly alive.
Something you should say 119.
Wait, that's Princess Bride, isn't it? Mostly dead,
He
but
isn't
he's
all dead.
No, but he was mostly dead, but he means he's partially alive. Wasn't that what he was
He
saying?
said, yeah. He said,
Have fun storming the castle.
your friend is mostly dead. There's a great difference between mostly dead and all dead.
He's partially alive.
He's
This is a
only-
great movie. So, should I ever graph these problems? No, but what could I use? I would use my calculator. So if I go back to my calculator and I go to my y equals table and I would put in 119.6 e to the 0.0917x, I think that's right. Year 0 is what year? 1972. What year would the number of species reach 1,000? So 72, it's just a matter of counting.
If you just hold it for a second.
24?
So after 20, so I would say the 24th year after 72, it turned over, okay? So what's, if year 0, 72, 73, 74, 75, so what is it? In the year of 1996, the number of endangered species in the United States should have reached 1,000. I wonder if that was true. Trap, Google that. You've got your computer open.
Or
Look for the number of Google number of endangered species in the United States in 1996. watched it was like 6. I'm sure it's more than that.
They don't have a desk.
Yeah. It was partially there. It's like the Simpsons episode when he's going back and forth in time, and he steps on the fish coming out of the water. You guys don't care. Careful, I'll make you watch that video again.
I'll go to the bathroom with them.
I didn't go to the bathroom because I didn't want to be here for the video. I went to the bathroom because it was better to go during that than while I was teaching.
Do those, please. Should be pretty quick. Okay. Double check those numbers, but yeah, it should be. How many were there, Trap? Come the Google machine isn't working quickly.
It is, but there's like no. Why can't there just be like one
Whoa,
answer?
whoa, that's a lot.
Seriously, there's like, is this growth or decay?
Oh, okay.
Oh.
All right, come on now.
I thought that it was like
Graphing
word
problems and
problems, and
stuff.
I was like,
No.
oh.
76 to 80. 76 to 80 of the word problems, but again, it's you're pressing buttons on the time. A couple of them. Yeah, the first, I don't know, 16 of them. What is e squared times e to the 4?
Wait, really?
Yeah.
Okay.
All right, just simplify the expression. And the reason why I was throwing that in there, because I just want you guys to remember how to simplify expressions. Because that'll come back again. It comes back again a little bit with logarithms. Let's do this then. I think I had planned out this week for us that we were going to quiz. What was I looking? On Wednesday? Once everybody's done, I'm still. Oh wait, no, I got the last person at 12th hour. Yes, I'll give it to you tomorrow. Okay, we'll do it tomorrow. No, because I don't have time to do it now.
Do you have 4 minutes? You have 5 minutes.
I'm trying to figure out quiz stuff here.
I'll pass it.
All right, we'll still quiz on Wednesday. What I'll do for tomorrow is we'll do a whole bunch of word problems and junk like that. I'll get some more growth decay stuff for us to look through. There is nothing to review.
Because we're quizzing on the
I'm
thing.
going to do it tomorrow because I don't have.
You
I
have
have
5
3
minutes.
minutes.
You have 5. We get out of 24.
5 minutes.
Emma, calm down. Murphy,
Yes, sir.
apparently 1179